Okay, let's settle in and get moving here. So I don't think I need to remind you, but again, you got an exam coming up next time we see each other on Tuesday. Get here on time. We've already gone over the format. This is really just a placeholder to remind you of these things. Remember, par score 1712, full page, pink in color. And make sure you're going to need to fill in your ID, write it in and bubble it in, your name, write it in, bubble it in, and the version. It will be either version A or version B, okay? And again, if you can do those things, you're going to get 2 easy points, okay? In terms of behavior, again, everything should be secured in your book bag. The only thing you're going to need is your pencil, eraser, and a Scantron, okay? That's it. You don't need a calculator, and you certainly do not need any other kind of electronic smart device. Don't get caught with it, okay? All phones should be off, all electronics secured and out of sight. If you have any doubt whatsoever, you're going to want to talk to me about it, okay? The other thing is, once you leave the lecture hall, you have completed your exam. No one is allowed to leave and come back. What does this mean? It means if you have to go to the bathroom or you think you might have to go to the bathroom, you're going to want to do that before you begin taking the test, okay? Besides which, it will make you a little more relaxed, and you'll be more in the frame of mind to worry about questions on the exam, okay? When you're done, you will hand in both your Scantron and the exam. Make sure your name is on both of them. It can be easy to get too caught up in the par score, filling in of all the information that you forget to put your name on the actual exam. But remember, that's where all your free response questions will be on the exam that I hand out to you. The par score will only contain your multiple choice answers. Any questions on that? I don't want to go over this stuff on Tuesday. I just want to get the exams out to you guys as fast as possible so you can take them, okay? All right. So the stuff we're talking about today will not be on the exam, okay? This is the beginning of the second portion, okay? And this is the beginning of what will be covered on exam 2. So we talked about cell-cell interaction, we talked about transporters, we talked about channels, and very importantly, we talked about membrane potential. That puts us in a very good position because I'm sure we all completely understand membrane potential now. And we all understand how inside the cell, the ionic environment is very different than outside the cell. Lots of potassium inside, lots of sodium outside, and we have this distinct electrochemical gradient where basically if potassium is allowed to move freely, it will leave the cell. And if sodium was allowed to move freely, it would enter the cell. This sets the stage for a very important part of physiology for understanding how the nervous system works by looking at the chief cells that run the nervous system, which are the neurons, okay? So the nervous system, as all scientists do, we love to divide things up into subdivisions. We can divide the nervous system into 2 very distinct areas based on location. The central nervous system, which is our brain and our spinal cord, and our peripheral nervous system, which are all the nerves that radiate off the brain and the spinal cord and service different parts of our body, okay? So tissue is composed of neurons that conduct impulses and glial cells that support the neurons, okay? Neuroglial cells are part of the nervous system. They are not the neurons, but they are the things that keep the neurons working very well, okay? And in fact, they're so important that for every single one neuron we have 5 glial cells on average supporting that neuron, okay? Because neurons, as you'll discover, are very high maintenance, high demand cells. They require to have this 5x support. So cells of the nervous system, as I just said then, neurons, and these are the ones that are responsible for receiving and sending electrical impulses. So in case you ever wonder, how does your nervous system actually work? It works through the power of electricity. Okay, a neuron will get a message from a neighboring neuron, and in response to that message, it will either create a little electric spark called an action potential, or it'll receive messages to not do that. And then the neuroglia are the cells that support the neurons. Okay, and here's just a cute little cartoon showing you here is your neuron in yellow branching out, doing all these cool little neuron things. And all around it are all these different cells, glial cells, that support that neuron. Okay, so when we look at neurons, one of the important things to understand, again, this idea of form and function. If we understand the shape or the form of something, we can learn an awful lot or infer an awful lot about its function. Okay? So neurons vary in size and shape, but they have a fairly common design. They have a cell body, and we can call them nuclei if they're in the central nervous system, or we can call them ganglia if they're in the peripheral nervous system. Okay, so like all things scientific and technological, there is a set of jargon associated with the conversations we're going to have about neurophysiology. Dendrites are basically these antennae that come off the cell body, and they are there to receive signals. Okay? And then the axons are these long cable-like projections off the cell body that are there to initiate and move a signal to another neuron or another part of the body. Okay? Here is a picture. This is the cell body. This is basically the metabolic center of the cell. All the stuff we talked about in a previous lecture, the nucleus, the ER, the Golgi, all of that stuff is in the cell body. Okay? The mitochondria, all of it. It's the cellular center. It's basically where the bread and butter of the whole thing. Out here are the antennae, the dendrites. They branch out like antennae. They branch out waiting to receive a signal either from a sensory cell or from a neighboring neuron. Okay? Right here is the axon, but at the junction between the axon and the cell body is a very important part of the cell called the axon hillock. This is where the almighty action potential that we're going to talk about and talk about and talk about is generated. And when the action potential is generated, it will travel through the axon. And you can think of this axon as a very, very tiny cable that is there to conduct and transmit an electrical signal all the way to the end, to the axon branches here, the terminal endings. Now, that's the basic structure. Neurons can look different based on their location, okay? So this is a neuron that is probably going to be located in the peripheral nervous system. This is a typical neuron you would see in the central nervous system, and your book goes into some detail about that. So the axons vary in length from a few millimeters to a meter. Now, I want you to think about that. We are still talking about one cell. Some of these neurons are so long that the axon itself is 1 meter in length. That's a huge portion of your total length, right? And we're obviously talking about a neuron that is coming off the central nervous system and probably traveling down your leg. That axon is one cell, and it travels a huge portion of just your leg. Okay, so you can see these are very complex cells, and they have a lot of demands that need to be met. The region, so we talk about the axon hillock. Some of these neurons, and you can see in this depiction here, the axons are covered with something. It's called myelin. Okay, and we're going to talk a little bit about myelin and why it's important. All axons in the peripheral nervous system have this myelination. Most axons in the central, but not all, have a myelin sheath as well. And we're going to talk a bit about that. Okay, so classification of neurons, we can give them different functional groupings. Sensory neurons, okay? I think we understand what a sensory neuron is. Something that is responsible for taking a signal that is received by one of our senses and moving it to the brain. Okay, and this is vital when you go back to that first chapter about homeostasis, sensors, integrating centers, and effectors. This is exactly what we're talking about. The sensor is one of our 5 senses that you probably have some familiarity with. That message has to be sent to the integrating center. What do you think the integrating center is? The brain, that big old thing we carry around on our head or in our head, okay? So that message is being sent by sensory neurons. We also call them afferent, okay? Afferent meaning heading towards the brain, all right? Then we have motor neurons. Motor neurons sort of serve the opposite side of the same coin. When our brain decides we need to do something, it needs to send that message out to the appropriate part of the body so action can occur. That message leaving the brain to that part of the body is leaving on what's called a motor neuron or an efferent neuron. So we have afferent heading to the brain, efferent moving away from the brain, okay? These motor neurons, as the name would suggest, are very important for our muscles. So our muscles are what will move us and give us motor coordination and motor abilities. However, they can also go to other parts of our body, inside our body, things like glands. They have to be under control as well. They are under the control of the central nervous system, and those messages are sent via motor neurons. Association neurons are also called interneurons, and these are the sort of in-between neurons, okay? Basically, an afferent neuron, a sensory neuron, will send a signal, and it will end somewhere at an association neuron or an interneuron. Then decisions will be made and then sent to the motor neuron. So in a sense, our brain is really nothing more than an enormous collection of association neurons or interneurons, okay? The complexity is that it has so many connections, we can't really understand what's going on entirely in the brain, but we know by sending these signals to association neurons and having them move to other association neurons, somehow decisions are made and then they are exported out via the motor nervous system, okay? Okay, so this is what it looks like anatomically. Here is the central nervous system, represented as the spinal cord. Okay, the spinal cord comes off the hindbrain and travels down our back on the vertebral column. And what do we have? Well, in here we have this association neuron, okay, which is strictly a central nervous system neuron. And then it is going to be sending the message out, or actually here it's receiving the message from a sensory neuron. And then it will also have the ability to send a message out on the somatic motor nervous system or the autonomic motor nervous system. So now I've just mentioned two different subdivisions of the motor nervous system that we'll have to talk about in a subsequent lecture, okay? But the motor system comes down to, is it under our conscious control? If so, it's the somatic motor nervous system. Or is it under what we call our autonomic control? I'm sure you guys are aware that your body does an awful lot of important work without consulting you, right? Luckily for us, when we go to sleep, we continue to breathe. Our heart continues to beat. Those are things that are controlled by the autonomic motor system, okay, meaning it's autonomous. It doesn't need our conscious effort to do these things. Lucky for us. Okay, so yeah, as I just said, two types of motor neurons, the somatic and the autonomic. And unfortunately for you guys, we can break the autonomic down into two other subdivisions, which is going to be the sympathetic and parasympathetic. So who here in the room has heard of the sympathetic motor system and the parasympathetic? We have a couple of like sort of nicknames we give them. Are you guys familiar with those nicknames? I think I heard it. What? Fight or flight, which is which one? Sympathetic, right. And parasympathetic, anybody know that one? Very good. Rest and digest, okay? It works 90% of the time. It describes them very well. Sympathetic, oh my God, something's happening. This vicious animal is about to eat me. I need to take action. The autonomic motor system, the sympathetic branch, will kick into gear. Your heart will start beating very rapidly. Your eyes will dilate. Lots of things will happen that will allow you to jump into maximum action mode, okay? Parasympathetic is the other side of that. If you're just chilling out and you don't really need to be wasting energy and maybe you want to get other things done like digest a delicious burger you just ate, the parasympathetic system is going to step in and take predominant control. Okay, A little bit more on vocabulary, neurons and nerves. They are not the same thing. Okay, nerves are made up of bunches of neurons. Okay, so basically nerves are a bundle of axons located outside the central nervous system. So again, we have this unfortunate habit of giving slightly different names to the same thing based on whether they are in the central nervous system or in the peripheral nervous system. So in the peripheral nervous system, we have nerves. Okay, most are composed of both sensory and motor neurons, and they're called mixed nerves. Okay, just as this wire, if you were to cut it open and remove the insulation around it, you would see it's a bundle of highly conductive strands of metal. Our nerves are very similar in that sense. This would be a bundle of axons, both afferent and efferent. Some of the cranial nerves have only sensory fibers, but that's just kind of an exception. And then if we have a bundle of axons in the central nervous system, we call that a tract. Okay? So you'll hear this language used based on whether someone's talking about the central nervous system or the peripheral. So the supporting cells I already alluded to, but basically neuroglia or glial cells. And we have two types that are predominantly found in the peripheral nervous system. Schwann cells or pneumocytes. And these are the cells that form these myelin sheaths that I showed you earlier. And then we also have satellite cells or ganglionic gliocytes. These support the cell bodies within the ganglia of the peripheral nervous system. What are ganglia again? What's that? Cell body, exactly, in the peripheral, right? Okay. So, supporting cells of the central nervous system, we have four chief types. We have oligodendrocytes. These are very interesting cells, and they perform a similar function as the Schwann cells in the peripheral. They basically provide the myelination for the axons, okay? But they look very different. The microglia, they just kind of move around, and they sort of are there to scour up things in the central nervous system that shouldn't be there. Okay, so they do that through phagocytosis, which we talked about. Astrocytes regulate the external environment of the neuron. We'll talk about that a little bit. They're extremely important for the well-being of our central nervous system. And the epidermal cells are basically these things that line the ventricles of the different compartments of our central nervous system, what we call cavities, and they secrete that all-important cerebrospinal fluid that our brain and our central nervous system is bathed in, okay? So this is just sort of a cartoon of that, and again, the yellow represents the neurons themselves. This guy with all the projections coming off of it, that's an astrocyte. Very important to realize the astrocyte is making a lot of intimate connections, not just with the neuron, but with this blood capillary, okay? So the brain obviously is a high-demand organ. It needs lots of energy. It needs lots of glucose. And it needs lots of oxygen, and it's going to come by the way of these capillaries, okay? The oligodendrocytes, which you see here, are very interesting because you have this major cell body, but then you have all of these extensions that come off, and they wrap around different parts of axons. That is the myelination that you see in the central nervous system. And you can see how one oligodendrocyte can be covering this myelination for more than one neuron. So they're very, very diverse in how they can do that. These are the microglia. These are the ones that sort of move around, and they eat up the things that shouldn't be there. If, heaven forbid, you've got some sort of pathogen in your central nervous system, you're going to want some cellular mechanism to get rid of it. The microglia can do that. Okay, so the neurolemma and the myelin. So now looking at myelination in the peripheral nervous system. And you can see here I'm using a lot of abbreviations. So PNS for peripheral nervous system, CNS for central nervous system. Okay. So basically these perform the same function as the oligodendrocytes, but they do it physically in a different way. They actually wrap around, the whole cell will wrap around an axon. Okay. And so this myelination is really important both for the central nervous system and the peripheral because it allows neural conduction, the action potential, to travel much faster due to the myelination. And if you're asking yourself, how in the world could that happen? Why is that? Don't worry, we're going to talk about that quite a bit in this lecture. And then the area between these areas of myelination, there's always a little area between one and the next one. That open area is called the node of Ranvier, okay, which is extremely important. So this is what myelination looks like if you're in the peripheral with a Schwann cell. This is the entire cell. So it's not like the oligodendrocyte that has a projection that goes off and grabs the axon. It actually is the whole cell wrapping itself around several times, okay? This is showing you where the nucleus is of the cell, and you can see it is wrapped around that part of the axon several times, providing myelination. Okay, and so this is what it looks like sort of in cartoon fashion, and it's providing this kind of insulation, just like you see with wiring in your house, right? Why do we have insulation around wiring? Yeah, to prevent the charge from dissipating and dispersing. You want the charge to move down the length of that wiring, not be dispersed and lost to the environment around it. That's what the insulation provides. This is also what the myelination is providing on a neuronal cellular level. Yeah. Yeah, that's a good question. Is there a difference in terms of how much coverage there is between one oligodendrocyte and one myelin on an axon? I don't know. Yeah, and I certainly, it's not anything I expect you guys to know. It's a good question. I can look into it. You might envision that, yeah, a Schwann cell is going to cover more linear distance, but I actually don't know that for sure. Yeah. Okay. And this, again, this is the artistic interpretation. This is what it looks like if you're a neurobiologist. This is how it was discovered, basically using electron microscopy. And you can imagine this axon is coming out and at you guys, and we do a cross-section. And when you look at it, you can see all these little rings, kind of like the tree rings you see on a tree. And then you can look, and you can see the nucleus and the cytoplasm as well that are surrounding it over here. Okay, so this is a really interesting feature of our central nervous system and our peripheral nervous system. So in the CNS, not all of the neurons are going to be myelinated, but many, many of them are. And again, this is done by the oligodendrocytes, and that is why, in case you've ever wondered, why when you look at a scan of the brain, we see two areas, right? We see gray matter and we see white matter. It's because of the myelination that you see those two colors, those two contrasts. The white matter is representing the myelin that is around the axons, okay, and it gives it that white appearance. And then the gray matter is basically the cell bodies of those myelinated axons, as well as axons that are not myelinated, okay? So that white comes from this covering that is going around the axons in the central nervous system. Okay, and again, this is what it looks like, kind of a dramatic artistic interpretation, but you have one cell reaching off in several directions, myelinating a portion of an axon, but also myelinating several axons at the same time. And then in between, you have this node of Ranvier. The node of Ranvier is a common feature to both the peripheral and the central nervous system. There are gaps along these axons between one area of myelination and another area of myelination. Now, because of these differences in what cells are doing the myelinating, whether you're in the peripheral or the central, there's an important difference between our ability to recover from injury on whether it happens in the central or the peripheral, right? I think we all have some recognition that central nervous system injuries are typically catastrophic. Okay, if you do some damage to your nerve tracts in the central nervous system, recovery is very, very difficult. Okay? However, in the peripheral nervous system, recovery is much more likely. Okay, and we've seen this, right? You hear of incidents where somebody is unfortunate enough to lose a finger or perhaps even a limb, and if not enough time has passed, it is possible to put that limb back on the person. There'll be regeneration not just of the muscle tissue, but regeneration of the actual neural tracking and the neurons in those two tissues. so that, even though I lost my finger, I could sew it back on quick enough, and I could still sense things, and I could still make it move because the nerves have regenerated adequately. The idea is why is there this difference is because the CNS axons may not be able to regenerate because of the vital function that is provided by the Schwann cells, but not the oligodendrocytes. Okay? And so in the peripheral nervous system, here is your axon, here are your Schwann cells, here's your node of Ranvier. You have an injury, and what's going to happen is all of this will degenerate, okay, through cell death, and then the Schwann cells will actually come back and guide the remainder of this axon to the direction of where it needs to go. And so it recreates sort of this tube of regeneration so that the axon can continue to grow back out to where it needs to go. Unfortunately, oligodendrocytes in the central nervous system can't seem to provide that kind of structure for the rehealing of a destroyed axon. Okay, astrocytes. Again, this is a support cell in the central nervous system, probably one of the most abundant supporting cells. And they have these really cool end-feet processes that basically go and connect and make intimate contact both with the blood vessel capillaries and the axon terminals, okay? So here you can see, here's the astrocyte reaching out, basically monitoring what's going on in this blood vessel, taking up nutrients. It can take a lot of those nutrients and then deliver it personally, so to speak, to the axon of a neuron, okay? Because again, these neurons are high maintenance things, and you can think about it as though these guys are personal assistants to neurons, okay? They don't give neurons the ability to do what they do, but they help neurons do all the things that they do, okay? So basically, they will take up potassium from the extracellular environment to maintain the environment for the neurons. They will take up extra neurotransmitter from the neurons. They will basically take up glucose from the blood, make ATP through glycolysis and the Krebs cycle, and then give that ATP to the neurons, okay? So you can see, because the neurons have such a high-end, high-maintenance job, having an astrocyte there to help the neuron do it is a tremendous help. Okay. It's also really important for the actual creation of our central nervous system. The astrocytes are so important that CNS neurons will not form unless astrocytes are already there. Okay, and the astrocytes are basically leaving a trail that the neurons can sense and say, okay, I want to move over in this direction because that's where the astrocyte is guiding me. Okay? You guys have heard of the blood-brain barrier? Anybody? Raise your hands. Okay? It's really critical because even though we're not going to get into immunology in this class, our brain, our central nervous system, is what's called immunoprivileged. Okay? And what that means basically is most things in our body are not allowed to get into our brain. Okay? Because it's just too important. It's the headquarters. It's where all the neuronal functioning happens, or all the decision-making neuronal functioning happening, the integrating center. Therefore, only things that have specific instructions to enter the brain are ever allowed to enter the brain. The astrocytes are basically the main enforcers of that because they have these end projections that cover the capillaries that bring the blood in. The astrocytes are actually there scrutinizing everything that wants to get in. So they're basically acting like bouncers for the central nervous system, okay? And if you want to get into it, you've got to leave this blood vessel, and then you've got to be able to get through these end-feet projections of the astrocytes to do that. Unfortunately, some pathogens have figured out ways to do that over the course of evolution and millions of years to wage this war and trying to figure out how to get around it. But for the most part, this blood-brain barrier is extremely effective for protecting our central nervous system. Okay, and that's what I just said. Okay, eye clicker. Fun fact. I saw this the other week. It has nothing to do with what I'm talking about, but it has something to do with physiology. So, you guys all ready? Remember, by the way, channel CD. Is everyone good with that? Okay. Let's see here. How many muscles do you use to take a single step forward? How many muscle groups? Yeah. Yeah, I'm using the word muscle, not as in muscle cell, because that's not what a muscle is. A muscle is a group of cells, yeah. So. Just a simple step forward. Okay, I'll give you 45 seconds. About there anyway. All right. So what do you guys think the answer is? D or E? Let's see here. Oh, wow, look at that. We do not have a majority. A very slim plurality thinks the answer is D. D is the answer. It's about 200. Hard to be exact, but it's about 200. So think about that as you're walking out of this classroom. And I put that up there because, remember, it's the motor nervous system that is doing this. So something as simple as a step forward, your brain is sending out a tremendous amount of information to 200 different muscle groups near simultaneously, telling them what to do. And remember, it's not just about the major muscle groups picking your leg up and moving it. It's about the antagonistic muscle groups, the groups in your other leg that have to relax to allow productive movement to occur. So 200 muscle groups are in on this conspiracy to get you to take a step forward, okay? And it is your brain that has to give them all directions. Your poor, poor, tired brain. Okay, moving on to electrical activity and axons. So we kind of went over some of the major players and some of the ways that we talk about the structure of our overall nervous system. So now we have to talk about the main actors, okay? These are the neurons, okay? The neurons and muscle cells, by the way, act an awful lot like neurons. There are major similarities, so we can talk about some of them with overlap. But basically, they do their job by changing their membrane potential. Okay, so this is why we had to go on Tuesday and talk about membrane potential. Okay, to understand how a neuron works or how a muscle works, you have to understand this electrochemical division of potassium and sodium and how their movement, one way or the other, influences how a neuron can do its job. So a cell that is able to massively manipulate its membrane potential, we call that cell excitable. Okay, it is an excitable cell. All of our other cells, they have membrane potential for sure, but they are not in the business of massively fluctuating it, okay? They basically stay at a steady minus 90 or minus 80. So this excitability is caused because the neuron or muscle cell will dramatically change its permeability to different ions. How do we change permeability to ions? What do we talk about on Tuesday? What's that? Well, that's how we change membrane potential, but what does that? These ions are not going to diffuse through the plasma membrane. So what allows a cell to change its permeability to ions? Yeah, channels. Transporters, channels, things of that nature. Mostly channels is what we're talking about in this regard, okay? Okay, so ions will follow what we call their electrochemical gradient. And remember, the electrochemical gradient are these two forces that sometimes work together and sometimes work in different directions. The force of electrical attraction, positive is attracted to negative and vice versa, and the force of the diffusive gradient. High concentration flows to low concentration. Okay, so the flow of these ions, we call that an ion current. Okay, so how do we measure this stuff? Well, here's like an old-fashioned depiction thing, of an oscilloscope. Nowadays, we have more digital and more high-tech ways of doing that. But basically, at rest, a neuron is what we call polarized. Polarized is a fancy way of saying it's more negative inside than it is outside, okay? It has a polarity. When the membrane potential inside the cell increases, and it's shown here by this upward deflection, we're going to call that depolarization. Take the time to know these words, okay? You will be tested on your knowledge of these words. You're going to need to know them so that you can explain other things. So again, membrane potential in this example is minus 70. If it gets less positive, or I'm sorry, more positive, less negative, and it goes up from negative 70 to say minus 50, we call that depolarization. If it goes in the other direction, down this way, we would call that hyperpolarization. It goes from negative 70 to something even more negative. We call that hyperpolarization. Now, if it's depolarized, say it's up here around 0, and it begins to go back down towards its RMP, which stands for resting membrane potential, then as it heads back down, we say it's repolarizing. Okay? So depolarization goes from negative to positive. Hyperpolarization goes from negative to even more negative. And repolarization is going from a positive deflection back towards the more negative resting membrane potential. Okay? Now, this is important because depolarization is excitatory. If you want a neuron to do something, like make an action potential, you have to depolarize it. Okay? You have to have this deflection where it goes from negative to more positive, relatively more positive. If you want to lock a neuron in place and make sure it does nothing, you hyperpolarize it. You take its negative RMP and you make it even more negative. Okay? Both of these functions are extremely critical for how our nervous system works, because our nervous system works in two ways: telling certain cells to do things and specifically telling other cells to do nothing. So inhibition is a really important part of how our nervous system works. Okay? So how do we get depolarization and how do we get hyperpolarization? Well, based on what I talked to you on Tuesday about, if we open a sodium channel, what does that sodium want to do? Sorry. I don't even know who's talking. I just hear little mumbles. Go inside the cell. Exactly, right? The electrochemical gradient says sodium, if given the opportunity, will rush into the cell. That's a positive ion going into a negative cell. What does that cause? It causes the cell to get less negative, and we would call that what? Depolarization. All right? Say it loud, say it proud. We know this stuff. All right, so how would we make a cell more negative? I mean, it's all up there, so you can just read it back to me. What's that? I don't know how to speak mumble. I'm sorry. Thank you. Hyperpolarization, how do we do it? Exactly, right? So potassium would leave the cell, right? Because if given the chance, the electrochemical gradient of potassium is such that if the channels for potassium open, it's leaving. Because the concentration inside the cell is so high, the diffusive gradient would move potassium out of the cell. Remember, inside the cell, potassium's like 140 millimolar, and outside the cell, potassium is 10 millimolar. That's a huge, more than 100-fold gradient. Potassium will leave. That means a positive ion will leave the cell. That means the cell will get more negative, and that is hyperpolarization. And as this gentleman also mentioned, you could achieve it a different way. Instead of having a positive ion leave the cell, you could have a negative ion enter the cell, and that's where chloride fits in. Because chloride's diffusive gradient is such that if given the opportunity, it will rush into the cell. Okay? So that's laid out right here for you. And this is how we get neurons to send action potentials, or how we tell them specifically to not send an action potential. Okay, now we're going to look at it in a little more detail. Changes in membrane potential controlled by changes in the flow of ions. And I told you on Tuesday, our cells are more permeable to potassium. And that means under resting membrane potential, we let potassium move around a bit. Okay, we have sodium and potassium ATPase to move it, but we also have channels that are what we call leaky, okay? Meaning we let sort of potassium move its way around the cell, okay? It becomes more permeable overall. We also have another kind of very important channel, potassium channel, called voltage gated. What do you think voltage gated means? Does it say there? It means, as it says there, right, that basically whether the channel is open or shut depends on the membrane potential of the cell, okay? So when you change the membrane potential of the cell, you change the environment that all those proteins, these channels, are working in. It is not a subtle thing to go from -80 to +5. That's a huge change in membrane potential. When you change membrane potential, you cause some of these channels to either open or shut. Therefore, we call them voltage gated. Okay, they're a channel or a door or a bridge, and they have a gate. That gate is shut under certain membrane conditions and open in other membrane conditions, okay? Okay, now sodium is different. I told you sodium is relatively impermeable. The cells do not have leaky sodium channels. Sodium is just not allowed to come in when the cell is under resting membrane potential conditions, RMP. But we do have very effective voltage-gated sodium channels, meaning if the membrane potential conditions are just right, sodium channels will open and let sodium move down its electrochemical gradient, meaning moving from outside to inside a cell, okay? Okay, this is what it looks like, by the way. Here is your artistic interpretation of a channel, and it's shut right there. And then something will happen, like the membrane potential. And remember, the lipid bilayer is an insulator, but it also conducts this electrical charge that's going on a little bit. And if the membrane potential changes, we get an action potential, this channel will open. And then whatever that channel is specific for, let's say in this situation it's sodium, sodium will come rushing into the cell. And then when the conditions change, this little ball and chain doohickey, very scientific description here, will basically loop around and put a cork on that. Okay? It will physically obstruct the channel, and this is really important because that channel is out of commission for a set amount of time. No matter what the membrane potential does, that channel is shut. Okay? And we call this a refractory period, very important component of the action potential. Okay, so we have a resting membrane potential. We are talking about an excitable cell. We have, let's say, -70 millivolts. By the way, don't worry about what the resting membrane potential is exactly, because it's different for all cells, and it's not something I'm really worried about. I just want you to know in general it's -70 to -90. And you have large negative molecules inside the cell, the fixed anion pool. We have our sodium, potassium, ATPase pumps. We have our differential permeability of membranes. And so at rest, we've got a cell that has a high concentration of potassium inside of it, and it is surrounded outside by a very high concentration of sodium, okay? So the stage is set for a wonderful, wonderful action potential, okay? This is the language of our nervous system, okay? Here is RMP. We will get something that will trigger this action potential, okay? A threshold event, okay? Now, once it is over this threshold level, the cell becomes fully committed to an action potential. The point of no return has been crossed, okay? What happens here is it hits the point where where some of the voltage-gated sodium channels will begin to open. And what's going to happen at that point? Will sodium enter or leave the cell? I hate it when I talk to myself and there's 170 people in the room. Will it enter or leave the cell? It will enter, and the cell will become hyper or depolarized. Depolarized. Awesome. And guess what? As it becomes depolarized, more voltage-gated sodium channels will open, which means more sodium will enter, which means the cell will become more depolarized, which means more sodium channels will open, which means more sodium will enter, and the cell becomes more depolarized. So this is one of those rare examples of a positive feedback loop. The event that occurs makes the event occur even faster in the next iteration, okay? And so this causes a very, very rapid depolarization. We go from minus 65 upwards to plus 35. So much sodium has entered the cell that for a brief moment in time, the cell is actually positively charged and no longer negatively charged. On an electrical level, this is remarkable, okay? So what happens then? How do we stop this freight train of depolarization? Just before it reaches the top of the action potential, the most positive value, we hit another important event. We hit the sweet spot where the voltage-gated potassium channels are now opening. And what's going to happen because of that? Not yet. Potassium what? Potassium goes outside, exactly. The voltage-gated potassium channels open, and because of the diffusive gradient, potassium says, I'm out of here. And it starts to leave very quickly, and that's a positive ion leaving. That means the membrane potential will begin to go back to something more negative. What do we call that? Repolarization. Awesome. All right. So now the cell is repolarizing, okay? And then at some point, the potassium channels will shut down, but not until it's actually gone beyond the resting membrane potential, which means the cell is what? For those of you that can read. The cell is hyperpolarized. The cell is now completely inhibited from doing anything else in terms of action potential generation because it's gone beyond the resting membrane potential and gotten more negative, okay? That which you see here is the anatomy of an action potential, okay? Now, of course, we can go in and dig in a little deeper, at least go through it again to reinforce the ideas. Threshold membrane, okay, so basically there's a stimulus, and sometimes this is a very, very soft stimulus, and it doesn't actually reach that threshold. That means no action potential. But the moment it hits that sweet spot that opens up the first few sodium channels, the action potential has now been initiated and it cannot be stopped, okay? And so as I said, a little bit of sodium comes in, causes a little bit of depolarization, causes a few more sodium channels to open, a little more sodium comes in, causing a little more depolarization, causing a few more sodium channels to come in, and on it goes in this positive feedback loop, okay? And so this is the beginning of the action potential, and then at some point, as it nears this peak, it will hit the threshold where the voltage-gated potassium channels will now open, and the diffusive gradient is such that potassium will begin to leave, and when you have a positive ion leaving the cell, it will get less depolarized, or as we would like to say, it will begin to repolarize, okay? And then this will continue, and what will happen, we'll go back, what will happen is it will overshoot. It's such an aggressive response that it overshoots the resting membrane potential and becomes more negative, and again, that is hyperpolarization. That is highly inhibitory. It stops the action potential from being generated until we get back to where we were through the action of other cellular transporters, such as sodium potassium ATPase, to redistribute the charges. Okay? So what you're looking at in this diagram is the action potential, and this is showing you the timing of different things happening. This is the timing of the sodium channels opening. This over here is the inactivation of sodium, so they begin to shut down. And then this is the potassium channels opening, and then the shutting down of the potassium channels. So it's showing you how these two basic types of channels are coming together to create this pattern of ion flow, which is basically what the action potential is. Okay? Okay. This is the same thing, showing it to you in different, slightly different perspective. The important thing here is a typical action potential is 1 millisecond in duration. Okay, what is 1 millisecond? How many of them are in a second? 1,000. Good, okay? It's really a time frame that we cannot perceive and do it any kind of justice, okay? But the important thing to think about is if we take a very simple system and we say we have a sensory neuron, we have one neuron, and that neuron goes directly to our brain, and then we have one neuron that goes to our muscle, right? Afferent, efferent. So if I throw something at you, what is the speed at which I would have to get it to move at so that you could not respond? Yeah, basically 2 milliseconds, right? Because you are physically constrained in your flow of information by an action potential, all right? Luckily for us, most things are not going to be coming at us at that kind of velocity. But it is why, you know, I think you hear magic tricks where somebody thinks they can catch a bullet. They cannot catch a bullet. Although if you're in cahoots with the person firing the weapon, I suppose you could have a signaling mechanism where you're already in action to catch it before the bullet is actually fired. But this is something, there was a famous magician in the 50s who was trying to do this. Spoiler alert, his life tragically ended when he did not catch the bullet. But it is something to think about. If I take something, you know, and I throw it at you, not that I ever would, I'm not that kind of person, but if I were to do that, think about the neural transmission of information by action potentials that has to occur for you to make all the appropriate motions to do something about it, either get out of the way or protect yourself. That simple step forward took you 200 muscle groups, right? The act of dodging out of the way of a speeding car is going to take you a lot more than 200 muscle groups, all of them getting their own unique action potentials by which to drive your muscles in a coordinated fashion to do something. This is remarkable chemistry, and it's all built on this super boring stuff I told you about how quickly potassium moves out of a cell and how quickly sodium moves into a cell. Okay, so you can think sodium and potassium are boring, but they are the reason you're all here today. Okay, so these boring chemicals play very, very exciting roles. All right. The other thing about action potentials is they code for information, right? An action potential will tell a muscle to do something or perhaps not do something. But there is no information in the height of an action potential, or what we would call the amplitude. Okay? An action potential always achieves the same amplitude, whether or not there's a huge stimulus to make that action potential or just a subtle one that barely gets it to the threshold potential. So the size of a stimulus will not affect the size of the action potential. It will always reach about 30 millivolts, okay? And the time of the action potential will always be the same, okay? The size of the stimulus will not affect the potential duration is what I'm saying there, okay? So here you have a weak stimulus, and here you have a strong stimulus. Think of it as a sensory neuron. You know, if you touch your skin a little bit, or if you hit it really hard, the size of the action potential will be the same, which is pretty remarkable, right? So where is information coded? Well, the stimulus intensity is coded by the frequency of the action potential, okay? How many action potentials can you fit in 1 unit of time? So here, this would be basically a soft stimulus, me going just like that. And then this, because the frequency is much, much higher, is a stronger stimulus. So you could basically say this is like, ouch, and this is like, oh my God, get me to the hospital. Okay? That's the information. That's how things are coded with our nervous system. Not the height of the action potential, not the individual duration of one action potential, but the frequency by which you receive several action potentials. Okay? And so here, soft stimulus, it doesn't even reach threshold, so there is no action potential. Here you have a slightly stronger one. Yeah, it sends out 4 little beeps, 4 action potentials. Here it hurts a lot, and it's sending out many, many in the same unit of time. Okay? Now, the one thing I wanted to get to is this refractory period. Okay, so here is our threshold, here is depolarization, here is repolarization, and we enter then over here to hyperpolarization. Because action potentials never change in their actual length of time for an individual action potential, they are refractory in nature, meaning here you have an absolute refractory period, which means once sodium is depolarizing the cell, another action potential cannot be initiated because the cell is too busy experiencing an action potential. Okay? Now over here, when we get to the hyperpolarization, we call it a relative refractory period, which means 99.9% of the time there will not be another action potential because those sodium channels are gated with a little ball and chain doohickey, as are the potassium channels. But if the stimulus is super, super strong, that can be overcome. But for the most part, it will not happen. Okay? This is really important because this sets into motion the directionality of an action potential. It can only move in one direction because as it moves in one direction, it can't go back the other way where it just came from because those cells are inhibited. They're in a refractory period. Does that make sense? Because obviously if we had neurons that could send action potentials in both directions, that probably wouldn't achieve very much. What we need is a neuron, a sensory neuron that's only sending it towards the brain, and a motor neuron that's only sending it away from the brain and towards the muscles. Okay? And there it is, our ball and chain model there. Okay. So I want to get into the cable properties of neurons and talk about the importance of myelination. And so the ability of neurons to conduct charges through the cytoplasm. So you have to remember, even though we keep talking about it like it's a cable, it's a cell. Okay? And cells really, in a lot of ways, are not good transductors of electrical charge. And so if you were to just look at the axon without any kind of myelination, action potentials would be extremely difficult to initiate and to maintain because all of this charge would basically be bleeding out of the cell every tiny little nanometer it traveled. So how do you get around that? You insulate it, right? And what's going to insulate the axon? The myelin sheath, right? Schwann cell in the peripheral nervous system, oligodendrocyte in the central, okay? And so what we say here is that the axons have very poor cable-like properties. By themselves, they do not insulate the electrical charge that they're trying to move down the length of their axon, but we have, luckily, myelination mechanisms by which to take care of that. If you look at axon or action potential in an unmyelinated cell, as you see here, you would basically have to make an action potential every nanometer of the length of the axon, right? Just to keep that electrical charge moving in a unidirectional way. This is extremely energy consuming and extremely slow and inefficient. So we do have some neurons, actually both in the peripheral and the central, that do not have myelination. But they are not going to be used for emergency situations, that's for sure, okay? And so what we would get here is very, very slow conduction if we just had an axon with no myelination. Luckily, we have myelination, okay? And so myelin provides insulation to the axon, and the speed of action, because of it, is much, much faster. We call this saltatory conduction, okay? Saltation means to jump, okay? It's really from a Latin-derived word. And what happens here is instead of making an action potential along every single increment of the axon, you wrap it up with this insulating material, the myelin, and what you do is you focus all of your channels and all the things that are necessary for an action potential only at these discrete gaps in the myelination. And this is what we call the node of Ranvier. In the node of Ranvier, you put all of your equipment, all of your potassium channels, all of your sodium channels, all of your sodium-potassium ATPase. You invest it there. It makes an action potential, and we say it jumps to the next node because you have nice insulation here, so it can do that. And this is what we call saltatory conduction. Okay, this is why the myelination of our neurons is incredibly important. If you can also change the conduction speed if we look at the diameter. So basically, if we increase the diameter, we can increase conduction speed because there's less cellular friction. But really, the main player in this is the myelination, okay, and the node of Ranvier construction. So if you think about it, because of having this investment in the machinery at the nodes and having the insulation in other places, unmyelinated fibers are going to transmit an action potential at 1 meter per second. Okay? You can almost run that fast. Right? I mean, that's not good for sending information to and from your brain. Okay? If you're going to use this to control some of your glands that are on a more relaxed schedule, that's not a big deal. Myelinated fibers, 100 meters per second. 100 times faster because of this construction, this physical construction of myelination and nodes of Ranvier. This is an incredibly important thing, and it gives our muscles and our sensory systems much, much quicker response times. Okay? Okay. And then the myelin sheath here is provided for by the oligodendrocytes. And so what I want to do, I was just so excited about our little experiment on Tuesday. I want to run one more experiment in the few minutes we have remaining. Here's the problem. I need some volunteers. And I know in a class this size, nobody wants to get up and help out. But I'm going to ask 20, well, let's start with 15 brave volunteers. Please come up front here. And I need at least 2 people who have a timing device. I'll tell you, don't worry. Come on, we got to go, people. This is a big experiment. You're going to like it. I'm going to prove to you that myelination and saltatory conduction works. And I'm not even going to hurt anyone. Come on, we can do this. All right. More people, come on. This isn't going to cut it. We need more people. Get up, move around, get those action potentials firing. Okay. Let's get 5 more people. All right, here we go. All right. Brave gentlemen are from all the way in the back. We do this like it's The Price is Right. Come on down. All right. So what I want is, okay, you 2 and you 3 over here. Stand in front of this group. Now, I got to say, the only thing you have to do that you might be uncomfortable with is you're all going to hold hands, okay? Okay, so, all right. You guys stretch out as far as you can. No, the back row stay put. The back row stays compact and tight. Yeah, all right. That's about the same length, right? So who's got the phone, the timer? We need a timer here. Do you have a timer? You have your phone? All right, I want you to be on the end. Yeah, and then if you have a timer, you have to be on the end. Yeah. Okay, cool. Yeah, you'll need it in your other hand. Yeah, okay. All right, so do you guys have any idea where I'm going with this? Good. All right. So how many people are in the back row? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we have 1, 2, 3, 4, 5 in the front. All right. So here's what's going to happen. I'm going to say go. And you two on the end, when I say go, you start your timer. And when I say go, I'm going to squeeze both of your hands. Now, when you feel him squeeze your hand, you will squeeze your hand to squeeze her hand. And then you will do the same down, and you will do the same, and you will do the same. And on down the line we will go. Who's going to get to the end quicker? The front row, right? Let's find out. Okay, you guys ready? My timer's ready? Okay, here you go. Sorry, I have to hold your hands for a second. All right, ready, set, go. Redo? Oh, okay. All right. But you guys get the drill now? Okay. We ready down there too? You okay? Good? Okay. All right. Ready, set, go. What'd you get? How much? 0.71. And what'd you get? 2.3. Huh? Let's try that again. We're scientists. We repeat. You guys ready down there? Okay, you guys all know the drill. Let's work as fast as we can, okay? Ready? Go. 1.8? 0.67. 3 times faster, right? Is it something like that? Okay, you guys are great. You did a great job. I think very good, very good. Okay. What we just represented there was the front row was saltatory conduction. They were jumping. They had, quote, nodes of Ranvier, 5 highly localized sections to transmit the signal, whereas the back row represented cable properties of the neuron without myelination. They had to keep regenerating and regenerating the action potential, i.e. the hand squeeze, and therefore the flow of information was way, way longer, and also it required more energy. How many muscles had to flex to get that same signal to the end of the line? A lot more, okay? So that was just a way to show you and hopefully help you remember this little exercise, the importance of saltatory conduction, myelination, and the importance of those nodes of Ranvier. Because, in closing, there are very, very serious diseases that occur when the myelination of our nervous system is debilitated, okay? And so what happens if you lose the myelination in your central nervous system? Anybody know? Think about the importance of your nervous system, the importance of fast neuronal transmission of information, and now you're losing that myelination in your nervous system. Your reaction's a lot slower, but there's a disease. Multiple sclerosis. You guys ever hear of it? Okay, so it's really, really important. And basically, if this happens, you have a dramatic overall effect on your health. And it's not in a good way, as you might imagine, okay? So it's very important. This myelination, the role it plays, super important for both neural transmission and in the peripheral nervous system for nerve regeneration, okay? All right, we are done here. Oh, wait a minute. No. One last eye clicker. One last eye clicker. Sorry to fake you guys out like that. Is everybody ready? This is a super important question. All right, we're getting quick responses. That's good. I'm not going to show this answer to the class, so don't worry. Okay, I'll give you to 30. All right, you guys have a good weekend. Study hard. The lecture videos when I was not here are on Beachboard, not on Panopto. Sure, just give me a second here.